Now I've just upload the lecture notes of chapter 11 to the Blackboard, so please download it. Okay, I will cover the first part of it probably today, and also I will leave the rest of the lectures to next week, and also there may be a makeup class. I will announce the time for you. Now, please note that next Tuesday is the course evaluation. So during the lecture, I will give you about 10 minutes or 10 to 15 minutes to do the course evaluation. So please come to do the course evaluation together. The university will have, or I think the university have already sent you a link for the course evaluation. So maybe it's good for us to do it together during the lecture. So just to remind you to do that, to express your opinion about this course. And also please be reminded that on the coming Monday, there will be your project presentation. So please come to the venue on time. Please come to the Zoom session on time. So please enter the Zoom session at least 5 minutes before 1:30. So you have some logistic to do. For example, the TA may ask you to upload the document, and so that takes time. So it's better for you to enter the Zoom session early. Okay. Now let's continue with our discussion on oscillation. We only have one section left for this chapter, and that is force oscillation. Now, in our previous discussion, we focus ourselves on oscillation that is without an external force. So the object actually oscillate due to the restoring force. For example, the force on the spring, or the force of gravity in case of a pendulum. So these are the force inherent with the system. But now we are going to study another very interesting phenomenon. We assume that the external force pushing the system. Okay, there is external forces exerting on the system. So that is called force oscillation. Okay, there is an external force which input energy to the system, so to maintain the oscillation. So that is what we are going to discuss about. And now, before going into the details, I have to make it clear that there are quite many different frequencies involved in this problem. The first frequency is, of course, the frequency of the natural frequency of the oscillation of the system, and I denote it by omega naught. For example, a pendulum will have its own oscillation frequency. A violin string, for example, may have its own oscillation frequency. It is a frequency that's the object oscillate on its own. So that's why it's called natural frequency. If it's undisturbed by external force, if it is displaced from equilibrium and released, then the system will oscillate with that frequency. Okay, so that's called natural frequency. But that natural frequency, assuming it to be simple harmonic, would be modified by the presence of damping. Okay, when there is a damping force, we have already seen that in the presence of a damping force, the actual frequency of the oscillation is actually smaller than the so-called natural frequency. So I have omega 1, which is the damped frequency, equal to square root of omega naught squared minus gamma squared, where omega naught is the natural frequency and gamma with omega naught is the natural frequency without damping, and gamma is the damping constant. Okay. Now we have still another frequency, because we now have the external agent shaking the system. Okay, we have a hand, or you apply the external force in whatever means to shake the system. So when you shake the system, when you assume that your shaking is a periodic driving force, then there is another frequency, and I call that frequency the driving frequency. It is the frequency in which the external force is applied on the object, on the system. Okay. Now, so we now have several frequency, and it happens that when the driving frequency omega is equal to the natural frequency of the system, then the amplitude of the vibration will become largest. The system will effectively absorb the energy from the vibrating source. And so the amplitude will go larger and larger until it goes to a very large value. And that is called the resonance. Resonance happens when you shake the system with a frequency omega that matches the natural frequency omega naught of the system. Okay, so that is the idea. So when omega is equal to omega naught, then we say that there's a resonance and the amplitude will be large. The system will oscillate with a large amplitude, will be shaking violently, and that is the phenomenon we commonly call resonance. Now, I just give you some example of resonance you might heard or you might have encountered in your daily life. For example, this is a swing, right? You play it when you are small. Now, when your father push you, okay, your father may like to push you, so you swing higher and higher, right? Now, but the father who pushes son such that with a frequency to match the natural frequency of the spring. Now, the father will not push the son irregularly, okay, but he will push the son in a regular manner, and that regular manner will have a frequency that match the natural frequency of the spring, of the swing. Every time there's the son swing backwards to the maximum height, the father push him, right? It's just like this. So the frequency that the father exert the force is actually equal to the natural frequency. If the father push him in a very irregular rate, not matching that frequency, then there would be some canceling of force. If the boy is now moving back and you push it in opposite direction, then some of the energy will be lost, right? And that would be not effective in increasing the energy and the amplitude of the system. So if you want to push him higher and higher, you have to apply force with a frequency equal to his natural frequency. Okay. Now, there's also another interesting phenomenon is about glass shattered by sound. Usually, you imagine sound will have not much energy, but if you have a loud sound and if the sound has a frequency that matches the shaking, the natural frequency of the glass vibration, then that may be a chance for the sound to shatter the glass. This is a common physics demonstration you see in some of this show or in a science museum. Also, if you have two tuning forks and they are connected to a so-called wooden box, a so-called resonant cavity, if you set one of the tuning fork into vibration, the vibrating air may transmit the vibration to another tuning fork. And since the two tuning forks may have the same frequency because they are of the same size, the transmission may be very effective. So you vibrate one tuning fork and the transmission is somehow transmitted by air to the other tuning fork. So the other tuning fork will vibrate. Now, so let's have an understanding of the frequency response. Suppose I plot the square of the amplitude against the frequency. Now, why do I plot the square of the amplitude but not the amplitude itself? Because as you remember, for example, a spring mass system, the total mechanical energy of the system is actually proportional to the square of the amplitude. Do you remember for spring mass system, the total energy is half Ka squared, right? Where K is the spring constant and A square is the square of the amplitude. it is not just proportional to A, it is proportional to A squared. So plotting A squared against omega effectively reflects the energy, the amount of energy in the system. Okay. So that's why we plot A squared against omega. And omega naught is the natural frequency. So if you shake the system with a frequency that does not match the natural frequency, the amplitude or the energy of the system will be small. But if you have a frequency omega equal to the natural frequency, then you see the amplitude will go to a very large value, and also the energy will also go to a very large value. And that is the resonant phenomenon. Now, if the peak is higher, okay, if the resonance happens, if the resonant effect is large, then the peak here will be high, right? It means that the system gets when its response to the resonance is is shake very violently, and it means that so the higher, sharper peaks means that the more energy of vibration and less dissipation is transmitted to the system. Okay. Now we first would like to handle this problem in the absence of damping. We want to simplify the problem a little bit at the beginning, so we could discuss it, the problem without damping, and in the later discussion, we will add the effect of damping. Okay. Now this is the equation of motion. The left-hand side is just ma, the mass multiplied by the acceleration, d squared x dt squared. The right-hand side, we are considering a spring mass system again. So the restoring force is minus kx, which is the force from the spring. Now we have the external force. The external force is your hand. You shake the block. Okay, this is external force. Now we do not have damping. We do not include damping at this moment. And when I divide this equation by the mass m, k over m is defined as the square of the frequency or natural frequency omega naught. So omega naught square is k over m. I put it here. And here on the right hand side, I have a new term, f over m. Now f is time dependent. Okay, f is not a constant force. For the constant force problem, we already have solved it before. But now the force is periodic, which means that it is also changing with time. I will assume it to change as a cosine function. So I assume that f is harmonic. Assuming something varying with time is a harmonic function means the function is a sine function or a cosine function. Okay, so I write the force F as an amplitude I call F naught, which is a constant, multiplied by the time varying cosine factor. So I have cosine omega t. Now you should note that I now have two frequencies. The first frequency is the natural frequency. It is due to the spring and the mass vibrate with the natural frequency, omega naught, which is equal to square root k over m. But now I also have another frequency that is a shaking frequency. The shaking frequency is a driving frequency I call omega. The two frequencies are in general different. Okay. So we have just a differential equation now. Okay. Because we have such a driving force, so this is a resulting equation. Now, let's assume a solution. Again, we don't find a general method to solve the equation, but we can solve that equation by trial and error. We have a trial solution. Okay, and we assume a trial solution in this form: a cosine omega t. Now, you should notice that I assume that eventually, somehow, the oscillator vibrates as a frequency of the driving force. It follows the driving force. Now, this makes sense actually. When you shake the system long enough, using a periodic force, eventually the system will follow your motion, right? So that eventually it will forgets its own frequency, but for your shaking. So that's why I assume that eventually, in a steady state, the solution X is varying with the driving frequency, but not the natural frequency. Okay. Now this is an assumption. We still have to verify by substituting this solution into the equation that this solution really works. Okay. This is we have to prove it. We have to prove that solution really works for this problem. Now the proof is easy. Why? Because we only have to substitute this into the equation and see under what condition will the equation be satisfied for all time t. So the second time derivative is easy. You differentiate the cosine twice. You go back to the cosine. But you have a negative sign, and also you extract a factor of omega squared. Okay, for one differentiation you get 1 omega, and for two differentiation you get omega squared, and there should be a minus sign upon two differentiation. Okay, so the left hand side is something like this: minus omega squared, a cosine omega naught t. The right hand side for this term we have minus omega naught squared, which is note that these two terms are different. A cosine omega t, and also I have the fourth term. The fourth term is f naught cosine omega t over m. Now immediately you can see the cosine factor cancel, leaving you an algebraic equation which is independent of t, right? The cosine factor, you see, they cancel on both sides. So that means the equation can indeed be satisfied for all time t, right? If the cosine factor does not cancel, then there will always be some time dependent in this equation, and you cannot guarantee that the equation can be satisfied for all time. Now the cosine factor has gone. It means that the equation, this solution can satisfy the equation for all time t, provided that the coefficients are related in this way, right? The coefficient a is related to the other parameter in this way. Okay, so now we can solve for a. Okay, this is simple. After the cosine factor has gone, what remains is a simple algebraic equation, which allow us to solve for a. Okay, so this is the a. A is f naught over m, 1 over omega naught square minus omega square. And the energy is proportional to a square. So this is the answer. Now somebody asked me, why do you make such an assumption that the object will eventually vibrate at the driving frequency? Now there's no guarantee that this will work. But I can see from the differential equation, if I put a cosine omega t here, okay, I can have a term on cosine omega t for all the terms that involve the x. For example, this term involves a cosine omega t, and the second derivative will also involve a cosine omega t. So the cosine omega t term can be cancelled on the equation. So that means this solution is going to work. Okay, now we look at the mathematics and we draw this conclusion from it. So and that means the system eventually will follow the oscillation with the driving force to vibrate at that frequency. Now let's see how a squared is related to omega. Now there's a singularity. A singularity means a squared will tend to infinity, and that happens when omega is equal to omega naught. When resonance happens, okay, the amplitude is infinite. Okay, now but physically we would not expect an infinite amplitude. This happens. This unphysical situation happens only because we haven't taken into account the damping force. So the system will absorb energy more and more and more and more, and eventually goes to infinity. But that does not happen in reality. In reality, there's always some damping force that dissipate the energy. So the amplitude will not go to infinitely large value. Okay, the singularity here reflects that we use a model that is not so realistic because we do not include the damping in this model. Okay, and when omega is far from omega naught, then you can see from this factor when omega and omega naught the difference is large, then 1 over omega naught square minus omega square will be small. And so the amplitude square will die down. Okay. Now, but it may be instructive to look a little bit more about the amplitude A. The amplitude A is depending on the frequency by this formula. Okay. Now we can analyze the situation in two regimes. The first regime is that below resonance, so-called below resonance. The driving frequency is smaller than the natural frequency. Now you see there's a factor of omega naught square minus omega square here at the denominator. So when omega is smaller than omega naught, this factor is larger than 0, and A is also larger than 0, right? So that means if the driving force varies with a cosine omega t, the displacement, which is A cosine omega t, it also vary with the same cosine factor because A is now positive, right? So A and F naught, they are both positive, so they both vary with a cosine factor. Okay, so they are in phase. When the driving force is maximum, the disturbance is also maximum. When the driving force becomes minimum, the disturbance is also minimum. X and F, they goes in phase. Okay. But what happens when I go above the resonance? What happens when omega is larger than omega naught? You can see from this equation that when omega is larger than omega naught, then A is more than 0. So the force is the same, but now X, the amplitude now has become negative. So for clarity, I write, to emphasize that A is negative, I write the coefficient, the amplitude A as minus the absolute value of A. Okay, I want to stand out the negative sign. So you can see F naught and A, they are of different sign, right? F naught is positive, but A is negative, which means that when F is maximum, then the displacement is minimum. They are always in anti-phase. Okay, when F is negative maximum, X is positive maximum. They are always in anti-phase. Okay, so they have a phase lag of we say 180 degree or pi. Pi, this angle corresponding to half of wavelength. So when one wave is maximum, the other wave is minimum, it corresponding to a phase difference of pi, or they shift relative to each other by half of a wavelength. So one wave become maximum, the other wave is at the same position is the minimum. Okay. In your high school study, you probably have learned about waves, right? When two waves are anti-phase, one or 180 degree out of phase, one of the waves is maximum, the other wave is minimum, right? So that when the two waves are opposed, you will have a complete cancellation, known as the destructive interference. Now, this is not a destructive interference, but this is only showing that the two quantity are out of phase. Okay, the force and the displacement, they are out of phase. Okay. Now let's have a more realistic model. Let's include damping. Okay, our previous model is actually quite unrealistic, and the amplitude will go to infinity at the resonance, which is not realistic. So let's have a more realistic model. We do it by introducing the damping force. So we introduce the damping force here. The rest of the term are just the same. We now introduce only one one more term to the equation, and that is the damping force. So again, for simplicity, we assume the damping force will be linear, and that goes as minus BV, where V is the velocity of the object. Now, so we divide the equation by m as before. Okay, so the second derivative of x, and then the same as the previous notation for damp oscillator, we define B over M as the constant alpha. Now, this definition we already have seen before in the section of damped harmonic oscillation, right? We already have seen it before. So again, we use this convention. So this is the constant alpha, which characterizes the amount of damping. And V is just the dt, right? And as before, we define K over M as omega square and omega naught square, where omega naught is the natural frequency. Okay. So it becomes such a differential equation now. And the right-hand side now have the external force divided by the mass M. Now, we actually have seen this equation before in the chapter, in the section of damped harmonic oscillator. The only new term that we have added to this equation is the external driving force. Without this driving force, it's simply reduced to the damped harmonic oscillator equation we discussed in the previous lecture. Okay, so we add this new term here. Again, we assume the driving force is harmonic. So F can be written as F naught cosine omega t. So the equation of motion looks like this. Okay. Now the problem is, can we assume a solution in the form of A cosine omega t as before? The answer is no. Okay. Why not? Because it does not work. It does not satisfy the equation. You cannot make it satisfy this equation. How do you know? Well, we can have a try. Now, if x varies as cosine omega t, okay, so x varies as cosine omega t in the equation, we have another cosine omega t on the right-hand side, because this is a variation of the driving force. So we have two cosine. And also, the second derivative of x is also a cosine. We ignore the sign, the minus sign, actually. But these three terms, they vary as a cosine. That is what happened without damping, right? But with damping, there's a problem. With damping, we have this additional term. That additional term involves the first derivative of the displacement. If the displacement is a cosine, then the velocity, which is the first derivative of the displacement, goes as a sine, okay? Or minus sine, okay? Anyway, now you can see it is impossible to satisfy this equation. If you make the coefficient of the cosine equal on both sides, then there's no way, because you only have one term, right? There's no way for us to make the coefficient of the sine to be 0. So there's no way for you to satisfy this equation. Okay, you can have the cosine term all equal, the right-hand side equal to the left-hand side. So you can cancel the cosine, but not the sine term, because we only have one sine term. Okay, and alpha is not 0, so there's no way for you to make it equal to 0 for all time t. So that means this solution does not work. Simply does not work. So how do we handle this problem? It happens that we can solve the problem by adding a phase, by adding a constant phase. Instead of just writing the solution in the form of cosine omega t, we write the solution as cosine omega t minus theta. Where theta is a phase, that has to be determined from the equation of motion. Okay, we assume a phase lag between the displacement and the force. So the force goes as cosine omega t but the displacement is not in phase with the force now, because there is a phase lag of theta. Okay, so the two curve must not be in phase. The two curves must be shifting relative to each other by the angle theta. Okay. Now, why do we expect that this adding the phase will solve the equation? The answer is simple. If you remember what we have discussed about for matching the initial condition, we have already shown you that adding a phase like this will be equivalent to saying that the solution can be written in this form. Now, if you know the combined angle formula, you expand the cosine omega t minus theta, then you have cosine omega t cosine theta plus sine omega t sine theta, right? So you make the constant a cosine theta as c and a sine theta as d. You end up with this equation. Okay, now this is so writing a phase like this will be equivalent to adding the cosine term and the sine term together. Okay, so you add these two terms together. So now you have both terms present in the solution. Now, if you have both terms present in the solution, that would not be a problem, because now you have both sine and cosine for dx dt. You also have both sine and dx for sine and cosine for the second derivative, and also for the x, right? So there's a chance for you to make the coefficient of the sine to be 0 and the coefficient of the cosine to be 0. Okay, so that's why you can solve the equation now. Now, somebody asked me a very intelligent question. Why don't we assume something like the previous damped motion? We don't have this factor, right? In the damped harmonic oscillator, we have this damping factor, which means that the amplitude will die down. Okay, but now we don't have this factor in this solution. Why? Now, because we are constantly shaking the system, we are constantly inputting some energy of the system, and it happens that after some time, the energy that we input to the system will just be equal to the energy dissipated by the damping. And when such a condition has reached, okay, the system will oscillate with a constant amplitude. So the amplitude will no longer decay with time. If we have constant energy input, and if that input exactly balance the energy dissipation, the system will vibrate with a constant amplitude. And this is called a steady state solution. Steady state means you have to wait some time for the transient oscillation to die down, and then you will have a steady oscillation. Okay, so what we are looking for in this case is not the general solution to this problem. The general solution will involve the exponential decaying factor, actually, I told you. But what we are looking at now in this situation is a steady state solution. We have to wait some time for the system to become steady. And in the steady state solution, we don't see this exponential factor because the energy we input just balance the energy dissipated by the damping force. Okay. Now, so in summary, what do we assume? We assume that a solution is of the same frequency of the driving force, right? The solution X has the same frequency as the driving force, but there's a phase difference between X and the force F. Okay. Now, but there's important things to note. If I write the solution in this form, And when I was talking about a simple harmonic oscillator, then A and theta are determined by the initial condition. Is that right? The initial velocity and the initial position. The two initial conditions will determine these two constants. That's what we have done in the simple harmonic oscillation at the beginning of the course, right? At the beginning of this chapter. But now A and theta are not determined by the initial condition. They are actually determined by the parameter of the differential equation. I have to substitute this solution to the differential equation, to this differential equation, and find out under what value of A and theta will the solution satisfy the equation. So that's why A and theta are determined by this parameter, alpha omega naught, omega f naught, and m. They are not determined by the initial condition. Why do we don't have the initial condition here? It's because the solution that we are looking for now is not the general solution. It is only a particular solution that describes the steady state oscillation. So the steady state oscillation does not involve the initial condition. It is only a steady state oscillation that the system stabilized after a long time. So it forgets about its initial condition already. If you insist on putting on the initial condition, then the solution will become very complicated. But I'm not going to talk about it in details in this course. It's somewhat complicated. But I can answer your question after the lecture. Okay. Now I put this in extension because I know that this is rather difficult for you. So I do not pretend that I will test it in the exam. I just mentioned to you on how to solve the equation. Now I can actually solve this equation by assuming x to be a superposition of a cosine vector and a sine vector. Okay, and the coefficient for the cosine I assume to be p, and coefficient for the sine I call it q. And be careful, the sine and the cosine varies with the frequency omega, but not omega naught. Okay, now let's have a shorthand. I write the cosine omega naught as c, and the sine omega naught I write at s. So the x is equal to pc plus qs. C and s they are time dependent. Okay, p and q are constant. They are constant coefficient. So I differentiate once. The c become minus s, cosine become minus sine, right? The sine become cosine, right? And when I do one differentiation, I have additional factor of omega coming out. So is that okay? We have done it for a lot of time. Okay. Now we differentiate twice. The sine become a cosine, okay? The cosine become a minus sine. Again, we still have another factor omega coming out. So totally we have omega 2 omega. So we have omega squared here. So I put all this, okay, back to this equation. Now you don't have to follow it step by step. I know that the calculation is a little bit tedious, but just understand the idea. After understanding the idea, you can do it yourself if you are patient enough. Okay. Now the idea is that we have x dx dt and d square x dt square expressed in terms of s and c, the sine and the cosine term. So I can put all this back to the equation, and I collect terms with the cosine factor. So I collect all the coefficient which goes before the cosine, and then I collect all the coefficient that goes before the sine term. Okay, so now I have two groups of term. One group of term goes with the cosine, the coefficient of the cosine omega t, and the other group of terms are the coefficient for the sine term. Okay, for the sine or cosine sine omega t. Okay, so these are the coefficient, and on the right hand side, the driving force involves a cosine, so I have F naught over MC. Now, so if this equation is to be satisfied, then the coefficient of the cosine must be equal on both sides, and the coefficient of the sine must also be equal on both sides. I have to make the sine coefficient to be equal to 0 and cosine term coefficient to be equal to 0 separately, because a cosine cannot be equal to a sine for all time t, so they are independent of each other. So if I set the cosine coefficient to be equal on both sides, I have this equation. This guy is equal to F naught over M. Okay, and this guy, the coefficient for the sine, because we don't have the sine on the right hand side, so this coefficient must be equal to 0. Now for the second equation, I can solve Q in terms of P. Okay, I collect terms with Q, and I find that Q is equal to alpha over alpha omega divided by omega squared minus omega squared, omega naught squared minus omega squared P. Okay, so I expect Q in terms of P. And so I can use this relation, I can use this Q to substitute into the first equation. So the first equation will become solely in terms of P. So I can solve P now. Okay, I replace this Q by this guy, and I collect the P of this two terms, right? So now the P can be solved. Okay. Now, I do not want to describe the calculation step by step. Okay, I just want you to show you the result, because the calculation is straightforward, although a little bit tedious. You can solve for P, obviously, right? And after solving for P, you just put P here, put your P here, and you can have Q. Okay, so the P and the Q are something like this. Okay, which is rather messy. Okay, but it's straightforward. The calculation is straightforward, but quite messy. Okay. So now I have the displacement. The displacement is PC plus QS, right? P is this, the cosine term, and then the cosine term, and Q is this. We have a common factor. This is the common factor, and we have the sine omega t. Okay. This term omega naught square minus omega square goes with the cosine, and this alpha omega goes with the sine, right? And all other factors are common factors, so I can extract them out. Is that okay? This is terrible. It looks terrible, right? But it's not difficult. You can manage it if you are careful enough. So what are we going to do now? We have a constant multiplied by cosine plus another constant multiplied by sine. So we can turn it into this form. We can turn it into the cosine with a phase. Okay. Well, how do we do it? Well, we have done it before. Okay. Now we draw a right angle triangle, and the right angle is here at this angle, and this angle I call theta. On the vertical side, I denote the vertical side as alpha omega, which is this. The base of the triangle, the length of the base of the triangle is omega naught square minus omega square. So now I have two sides, right? And the hypotenuse of the triangle is, of course, this square, this term square, plus this term square, square root, which is this guy. Okay. Now, so if I want to write omega naught square minus omega square, I can actually write it as a hypotenuse multiplied by what? Multiplied by cosine theta. Okay. The hypotenuse multiplied by cosine theta. And alpha omega is just the hypotenuse multiplied by sine theta. Okay. Now, so I can rewrite this two term as a square root. The first one is cosine theta. The second one is sine theta. So I can extract the square root out, right? And the square root actually cancel with one of this, okay, leaving a square root at the denominator, okay, because this guy at the numerator denominator is exactly the square of the hypotenuse. So when I extract this factor out, it cancel one of this. It's cancel a square root. So leaving a square root of this at the denominator. And inside the square bracket, I now have cosine omega t, cosine theta, plus sine omega t, sine theta. But that by compound angle formula is exactly cosine omega t minus theta. Is that okay? Now here comes the final step. The final step is like this. I now have the amplitude now. The amplitude is given by A, given by this, right? This is the amplitude A. So A is equal to what? F naught over M, 1 over square root, omega naught square minus omega square, complete square, plus alpha square omega square, which is very complicated. And how about the angle theta? How about the phase? The phase is just arctangent alpha omega over omega naught square minus omega square. So we have the phase like this. So that completes the solution. Now, if you find the proof very complicated, don't worry. I will not test you this in the exam, but just focus on the meaning and its application. Okay, I want you to understand essentially the behavior of this curve, and if you cannot manage with the derivation, that is not important. Okay. Now, so this is a particular solution. Okay. Now, let's have a break at this moment, and when we come back, we will continue our discussion with this solution to see